Section: Introduction. In this section, we explore the concept of compound AI systems, also known as AI agents, which are gaining significance in research. Researchers suggest that compound AI systems will likely be crucial for maximizing AI outcomes in the future and could be a major trend in AI by 2024. Several agent benchmarks have been introduced across various domains like web interaction, programming, and tool usage. These benchmarks, initially developed for evaluating large language models, LLMs, are now being used for agent assessment. Agent evaluation differs from language model evaluation in significant ways. Agents are utilized for more challenging tasks that are realistic, have practical utility, and often do not have a single correct solution. For instance, agents can perform tasks using the command line, with some even having their own agent-computer interface. However, using agents can be more expensive than a single model call. To address this, cost control is essential in agent benchmarking. Our study highlights 5 key contributions. Firstly, we emphasize the importance of cost control in AI agent evaluations. Secondly, we introduce 3 new simple baseline agents that outperform complex agent architectures on certain evaluations while being more cost-effective. Thirdly, we advocate for jointly optimizing accuracy and cost for better agent design. Fourthly, we discuss the distinct benchmarking needs of model developers versus downstream developers. Lastly, we address the lack of standardization and reproducibility in agent evaluations. In the realm of AI, agents are entities that perceive and act within their environment. In the context of language model-based systems, the term agent is viewed along a spectrum rather than a binary definition. We identify 3 clusters of factors that contribute to an AI system being considered more agentic: environment and goals complexity, user interface and supervision requirements, and system design patterns like tool use and planning strategies. Overall, our aim is to encourage the development of AI agents that are not only accurate on benchmarks but also practical in real-world applications. By incorporating metrics beyond accuracy, improving benchmark precision, and ensuring reproducibility, we strive to enhance the utility of AI agents in practical scenarios. Section Summary. In this section, we explore the concept of AI agents within compound AI systems. We discuss the factors that define an AI system as more agentic, such as the complexity of its environment and goals, the level of user interface and supervision required, and the system design patterns it employs, like tool use and planning. These factors contribute to understanding the evolving definition of AI agents in the context of language model-based systems. Section: AI agent evaluations must be cost-controlled. In this section, we focus on evaluating AI agents while keeping costs in check. We understand that striving for maximum accuracy without considering costs can lead to unlimited expenses. By repeatedly using language models and taking a majority vote, we can significantly boost accuracy across various benchmarks like GSM-8K, Math, Chess, and MMLU, Sun_EasyHard_2024. When the environment provides easy signals to verify correctness, retrying can lead to even more remarkable performance improvements. For instance, AlphaCode's accuracy surged from nearly 0% to over 15% with 1,000 retries and exceeded 30% with 1,000,000 retries. This accuracy is measured by how often one of the top 10 answers provided by the model is correct. It seems that there is no cap on the amount of computational power that can enhance accuracy, and increasing the generation budget has proven beneficial in different applications. In coding competitions, correctness signals such as test cases are commonly used to validate solutions. Developers can continue sampling from a model until a solution passes all test cases. Our findings demonstrate this to be true for human eval. We illustrate the trade-off between accuracy and cost using a Pareto curve. Recently, many agents have been claimed to achieve top-notch accuracy in coding tasks, but at what expense? To explore this trade-off, we re-evaluated the accuracy of 3 agents, LDB, LATS, and reflection, from the human eval leaderboard on papers with code. These agents execute the generated code and debug it if it fails the provided test cases, exploring alternative paths in the code generation process or reflecting on why the model's outputs were incorrect before generating a new solution. We also assessed the cost and time requirements of running these agents and compared them with simple baselines like GPT 3.5 and GPT 4 models. We employed strategies like retry, warming, and escalation to enhance accuracy while managing costs effectively. Our two-dimensional evaluation revealed surprising insights, showing that state-of-the-art agent architectures for human eval do not necessarily outperform basic baselines. The cost of running these agents varies significantly, with almost a 100-fold difference in cost for similar levels of accuracy. Notably, the cost of running agents is often not a prominently reported metric in research papers. Furthermore, the lack of evidence supporting the effectiveness of more complex approaches like planning, reflection, and debugging, referred to as System 2 inches approaches, raises questions about their actual impact on code generation accuracy. The community's belief in the efficacy of these approaches is not adequately supported by empirical comparisons with simpler strategies. This lack of reproducibility and standardization in evaluating agents hinders the identification of sources of performance improvements. While System 2 techniques may prove valuable in more challenging programming tasks beyond those in human eval, such as SWE bench, it remains uncertain whether they are truly beneficial for code generation. In conclusion, effective agent evaluations should prioritize cost control, even if the primary focus is on innovative agent designs rather than cost considerations alone. Simply aiming for higher accuracy may not signify real progress if achieved through methods like repetitive retries that lack scientific significance. Section Summary. In this section, we emphasize the importance of cost-controlled evaluations for AI agents. We demonstrate that repeatedly calling language models and taking a majority vote can significantly boost accuracy across various benchmarks. By visualizing the accuracy-cost trade-off using a Pareto curve, we reveal that complex agent architectures do not necessarily outperform simpler baselines, highlighting the need for thorough evaluation methods that consider both accuracy and cost. Section. Jointly optimizing cost and accuracy can yield better agent designs. In this section, we explore how jointly optimizing cost and accuracy can enhance agent designs. By visualizing the cost and accuracy trade-off using a Pareto frontier, we can create agents that are cost-effective while maintaining accuracy. This concept can be extended to other aspects of agent design, such as latency. The total cost of running an agent includes fixed costs, which are one-time expenses for optimizing the agent's parameters, and variable costs, which depend on the number of input and output tokens. Joint optimization allows us to balance these costs by investing more upfront in optimizing the agent's design to reduce the variable costs of running the agent. To demonstrate the benefits of joint optimization, we modified the DSPY framework and tested it on the Hotpot QA benchmark. We used the Optuna framework for hyperparameter optimization to find few-shot examples that minimize cost while preserving accuracy. Our approach serves as a starting point to explore the vast design space enabled by joint optimization. In evaluating agent performance on multi-hop question-answering tasks using DSPY, we tested 5 agent architectures: uncompiled, formatting instructions only, few-shot, random search, and joint optimization. These agents were evaluated on the Hotpot QA task using different underlying models. Our results show that joint optimization can reduce costs while maintaining accuracy. By optimizing the agent's design, we can achieve significant cost savings without compromising performance. This trade-off between fixed and variable costs is crucial for efficient agent design, especially for large-scale real-world tasks where variable costs dominate due to frequent agent usage. Section Summary. In this section, we explore the concept of jointly optimizing cost and accuracy in agent design. By visualizing the cost and accuracy trade-off as a Pareto frontier, we can create agents that are cost-effective while maintaining accuracy, especially by balancing fixed costs, one-time expenses, and variable costs, per-use expenses. Through joint optimization, we can significantly reduce variable costs while preserving accuracy, as demonstrated in our evaluation on the Hotpot QA benchmark using different agent architectures and models like Llama 3-70B and GPT 3.5. Section: Model and downstream developers have distinct benchmarking needs. In this section, we, as model and downstream developers, have different needs when it comes to evaluating AI systems. Model developers and AI researchers use evaluations to improve accuracy, while downstream developers use them to choose AI systems for their products. The distinction between model evaluation and downstream evaluation is often overlooked, causing confusion about how to consider the cost of running AI. For model evaluation, which is of interest to researchers, it is common to focus on factors like parameter count or compute usage rather than dollar costs. By normalizing the compute used to train a model, researchers can determine if improvements are due to changes in architecture or data, rather than just increased compute. On the other hand, downstream evaluation, which helps with procurement decisions, focuses on cost. While cost measurement may not be crucial for model evaluation, it is essential for downstream evaluation as inference costs can change over time and impact developers' decisions. Using proxies like the number of active parameters or compute usage to represent cost can be misleading for downstream evaluation. For instance, a model may appear cost-effective based on these proxies, but in reality, it could be more expensive to use. Addressing challenges in cost evaluation is important. Different providers may charge varying amounts for the same model, and costs can fluctuate based on various factors. Providing customizable evaluation results that allow users to adjust costs based on their preferences can help mitigate these challenges. When designing benchmarks, such as the novel QA benchmark, it's crucial to consider the differences between model and downstream evaluation. While novel QA is suitable for model evaluation, it may not accurately reflect the cost implications for downstream developers. For instance, evaluating language models based on all questions about a novel at once may not align with how users would ask questions in real-world scenarios, potentially leading to misleading cost estimates. To ensure accurate downstream evaluation, benchmarks need to be tailored specifically for that purpose or be variations of existing model evaluation benchmarks. This separation is essential to provide relevant and reliable information for developers making procurement decisions. Section Summary. In this section, we differentiate between model evaluation and downstream evaluation, highlighting that model evaluation focuses on scientific questions like accuracy improvements, while downstream evaluation is crucial for procurement decisions based on cost considerations. We emphasize the importance of considering cost in downstream evaluation, as factors like inference costs can significantly impact developers' decisions on which AI systems to use. Additionally, we discuss challenges in benchmark design using the case study of novel QA, illustrating how benchmarks tailored for model evaluation may not accurately reflect the cost implications for downstream developers building practical applications. Section: Agent benchmarks allow shortcuts. In this section, we discuss the importance of agent benchmarks and how they can sometimes allow shortcuts. Benchmarks are valuable when they provide us with an idea of how well an agent performs in the real world. However, if a benchmark allows shortcuts, the accuracy achieved on the benchmark may not reflect the agent's performance in real-world scenarios. One common shortcut is overfitting, which is a significant issue for agent benchmarks, especially since these benchmarks are often small, typically containing only a few hundred samples. Overfitting is more problematic for agent benchmarks compared to contamination in the training data of large language models, LLMs. This is because an agent can directly incorporate knowledge of the test samples into its programming when using a lookup table, potentially achieving 100% accuracy on many agent benchmarks. Detecting overfitting is easier when an agent relies on a lookup table, but it can be more challenging to identify other types of overfitting that are subtler and harder to detect. This is why having held-out test sets is crucial in machine learning, yet surprisingly, many agent benchmarks do not include them. Developers creating benchmarks should not only establish a test set but also consider keeping it confidential to prevent contamination or overfitting by agents. Additionally, it is essential to consider whether an agent is overfitting to a specific task. For instance, if an agent performs well on a Python programming benchmark but struggles with other languages, it may be a concern depending on the agent's intended purpose and the benchmark creator's goals regarding the agent's versatility. We have identified 4 levels of generality in our survey: distribution-specific, task-specific, domain-general, and general-purpose benchmarks. Each level aims to assess the agent's ability across different tasks and domains. It is crucial for benchmark developers to ensure that the held-out set differs sufficiently from the training set, especially for benchmarks intended to be more general. This helps prevent agents from taking shortcuts that only work for specific tasks in the dataset, leading to poor performance on other tasks within the domain. Creating benchmarks that level the playing field has been instrumental in the significant advancements in machine learning over the past decades. While it may be challenging to anticipate and model all types of distribution shifts, benchmark developers should strive to identify the most likely shifts for the task at hand. Evaluating Sim2 Real Transfer, where agents are tested on real-world tasks in addition to benchmark tasks, can provide valuable insights into an agent's performance. Our analysis of 17 agent benchmarks revealed that most fall into the task-specific or domain-general categories. However, there is often ambiguity regarding the intended level of generality by benchmark developers, making it difficult to draw definitive conclusions about well-performing agents. We acknowledge that time and resource constraints may hinder benchmark designers from creating appropriate held-out sets, but it is crucial for the validity of the benchmarks and the agents evaluated on them. Section Summary. In this section, we discuss the importance of agent benchmarks and the potential shortcuts they may allow. Overfitting, a common shortcut, poses a significant challenge for agent benchmarks due to their small sample sizes. We highlight the necessity of including held-out test sets in benchmarks to prevent shortcuts and ensure the generalizability of agents across different tasks and domains. Section: Case Study of the Step Agent on Web Arena. In this section, we will discuss a case study of the Step Agent on Web Arena. Web agents are assessed based on various abilities such as navigating websites, scrolling, and selecting the correct web elements. Web Arena, an agent benchmark, contains clones of 6 different websites and 2 tools, with a total of 812 tasks for agents to interact with these sites. The main focus of Web Arena is realism, aiming to make it challenging to take shortcuts. One important aspect for agents is to be robust to changes on websites over time, known as drift. However, Web Arena does not explicitly model drift, which can make it difficult to evaluate agents effectively. The top agent on the Web Arena leaderboard, Step, achieves a high accuracy of 35.8% by hardcoding specific policies for the tasks in Web Arena. While this approach may seem effective, it can be fragile if websites change their structures, leading to policy failures. The goals of Step developers differ from those of benchmark developers, as Step focuses on fixed tasks with predefined solutions. This discrepancy can mislead developers who rely on the leaderboard accuracy to choose agents for real-world applications. Web Arena lacks a held-out test set to assess agent performance on unseen tasks, which raises concerns about the true reflection of leaderboard accuracy. If new tasks were introduced, the accuracy of agents like Step would likely decrease significantly due to their hard-coded policies becoming ineffective. Additionally, agent benchmarks often do not consider human involvement in task performance, which can vary from full control to minimal intervention. Evaluations typically focus on extreme scenarios of no supervision or complete autonomy, neglecting how humans interact with agents in real-world settings. Human-in-the-loop evaluation is crucial for understanding the true usefulness of agents, as human feedback can significantly improve performance. However, implementing such evaluations can be challenging and costly, as the accuracy of agents depends not only on the system but also on the expertise of human users. Despite these challenges, incorporating human-in-the-loop evaluations is an important direction for future research, especially in the context of safety evaluation. Section Summary. In this section, we explore a case study of the STEP agent on Web Arena, a benchmark for evaluating web agents on various tasks across different types of websites. The STEP agent achieves high accuracy by hard-coding specific policies for tasks, but this approach may be brittle and not robust to changes in website structures over time, highlighting the challenge of modeling drift in benchmarks like Web Arena. Additionally, the lack of a held-out test set in Web Arena raises concerns about the accuracy of agents like STEP on unseen web tasks, emphasizing the need for more comprehensive evaluation methods that consider human-in-the-loop interactions to better reflect real-world usage scenarios. Section. Inadequate benchmark standardization leads to irreproducible agent evaluations. In this section, we identified various issues with the standardization of agent benchmarks and evaluations. Our analysis focused on the importance of reproducibility in agent evaluations, where the code and data provided should be adequate to replicate the reported results. Without reproducible evaluations, it becomes challenging to differentiate genuine enhancements in agent designs from evaluation discrepancies. This lack of reproducibility not only misguides developers using agents in real-world applications but also consumes significant time for researchers attempting to build on cutting-edge results. We pinpointed 5 main reasons for the absence of standardized and reproducible agent evaluations, all stemming from differences between language model, LLM, evaluation and agent evaluation. These issues primarily fall under the responsibility of benchmark developers rather than agent developers. Evaluation scripts often assume specific agent designs that may not apply to all agents, leading to inconsistencies. Additionally, repurposing LLM evaluation benchmarks for agent evaluation can introduce inconsistencies and require modifications to the benchmark design and evaluation process. The high cost of evaluating agents, especially when they interact with dynamic environments, makes it challenging to estimate confidence intervals. This cost limitation often results in evaluations lacking error bars, hindering the understanding of result variance. Furthermore, the reliance on external factors in agent evaluations, such as interactions with environments, can introduce subtle errors. For instance, assumptions of task independence may not hold in scenarios like Web Arena, impacting the evaluation of agents like STEP. The lack of standardized evaluation frameworks has led to bugs in agent development and evaluation processes. To address these issues, clear standards for providing agent evaluation scripts are needed, along with a better understanding of the differences between model and agent benchmarks. Developing a dedicated agent evaluation framework is crucial for future advancements in this field.